presentation today is on an automated 3D print farm.
Hi everyone, thanks for coming out to our presentation. This is the automated 3D printer farm, MQP. My name is Dasad Bastandi.
My name is Lauren Podran.
My name is Zara Shujiro.
My name is Kevin Valente Comas.
So this is just going to be a brief outline of our presentation. I'll go through an introduction, a little bit of background. I'll go on to the motivation and goals of our project, methodology, the outcome, results, the next steps that we think future MQPs can take hold on, and then a short Q&A session. So I'll cover briefly the terminology that you'll hear a lot over the course of this presentation. Fused filament fabrication, that is the official phrase for what 3D printing is, FFF for short, and that's the idea of taking a thermoplastic, heating it up, extruding it through a heated head, which goes onto a print bed. That thermoplastic is known as filament. We use polyolinic acid, which you probably heard before is PLA. The print bed, as shown in this image right here, is often heated to provide better adhesion. A slicer is a software that takes a 3D model, often in STL format, converts it into G-code, which is labeled right here, and that is language that your 3D printer understands and converts into machine motions. So why do we use 3D printing? First of all, it's typically seen as a prototyping type of tool. You don't really see it as a production technology, and we want to use it as a small volume production run. So a 3D printer farm makes use of that. 3D printers really have power in numbers, and if you have a part request where you want to make 100 parts and each one takes 1 hour, you're going to have 100 hours of printing. If you have just 2 printers, no matter how good your one is, it's still going to take 100 hours. But if you have 2, you can cut your time in half. So technically speaking, a 3D printer farm is a collection of printers that are connected by a common server. This still requires manual servicing, and I'll get into why that's important in the next few slides. It's also still a versatile manufacturing service from a business perspective. You can make very complicated models, but you can also do small volume production with the farm. Here is a sample image using Prusa i3 printers. They're inexpensive printers. I don't even know, I haven't even counted how many are in this image, but they're all connected on the same server, and they're all able to be delegated prints.
So we have 3 key motivations. Our first was to increase campus accessibility. We want to make it so you could access 3D printers to the campus. Second was to reduce request turnaround time. The faster the system is, the shorter the standby time of the printers are between prints, the faster you can get prints done and more prints can get done in a time frame. Our last one was to increase staff availability. With this project, if it was to be implemented, a staff member would be able to spend less time on 3D print and spend more work with the students and faculty.
And that image in the bottom right, the monoprice maker Select V2 is actually the printer that we selected, and it has a nice price range of under $350. So it's perfect for this, and we'll be donating to the 3 printers that we use to WPI in the future. The goals of our project were fourfold. So primarily, we want to manage multiple print requests. We have a lot of students here. Rapid prototyping is becoming more and more popular, so we need to manage all these requests in a timely manner. We also want to be able to monitor the printers remotely instead of having staff personally available to watch them all the time. We also needed a way to interface the printers to the server and the robot. And finally, the most important part is taking out the human side of it and automatically removing, storing, and replacing these print beds. This image here is just a reference so you kind of understand what I'm talking about. You have the robot in the center with an end effector on it. You have 3 3D printers here, and then the server is hosted behind these 2 printers. And it's just what the setup looks like, and this is where we spend a lot of time in the lab.
So to manage our print requests, we use a package called MQP server, and what it allows us to do is we can access any printer that's connected to the system remotely wherever we have internet connection. We use the Raspberry Pi distribution of the software because it was light and compact.
So communication between our three 3D printers and our Raspberry Pi, which held the Repetier server, was done through USB ports. Communication between the Arduino, the Raspberry Pi, and the FANUC was done through TTL, or transistor logic, which is some basic electrical logic, which uses AND OR gates as well as amplifiers. Due to the three having different voltage ranges, communication between them had to be level shifted. For Raspberry Pi to Arduino communication, this did not need to be level shifted due to Raspberry Pi communicating within Arduino levels. However, Arduino to Raspberry Pi communication had to be level shifted down from 5 volts to 3.3 volts. FANUC to Arduino had to be level shifted down from 24 volts to 5 volts, and Arduino to FANUC had to be level shifted up from 5 volts to 24 volts.
There's actually kind of a funny story regarding the FANUC communicating with Arduino, but I'll save that for the Q&A session.
And this is the workflow of our system. Basically, the user sends a G-code sliced from a CAD model to the Raspberry Pi, to the Repetier server on the Raspberry Pi, which then sends the print job to one of the 3D printers. Once that is done, it communicates to the Repetier server, which then in turn communicates with the Arduino, which communicates with the FANUC, telling it which 3D print service and which shelf it should replace. It should grab the print bed to replace. The FANUC then communicates with the Arduino once it's done, and the Arduino communicates with the Raspberry Pi, which then frees up the 3D printer to accept more 3D prints.
So how we physically handle the print beds, this was a small mechanical electrical engineering problem. We had available to us a FANUC LRMA 200IB, is a late 90s 6-degree of freedom robotic arm. Uses a proprietary language on a teach pendant, and you can do offline programming, although it's just easier to be in person having this pendant in your hand. You can manually jog the robot around, set a position, and actually how I programmed it was one set of motions for going in, picking up the plate, turning on the electromagnetic solenoids to make sure the print bed doesn't move around during motions, and then dropping it off. That whole suite of motions was able to be copy and pasted essentially by telling the robot, there are 3 printers here, and here are their coordinates in 3D space. Replicate the motions and make the adjustments for the split frames. We communicate with the FANUC using data I/O lines. As previously mentioned, they're 24 volts, and that's that. I'll move straight to the results because, well, we actually have really good results. Excuse me. The print requests are queued and delegated to the printers according to the server just fine. We have never had a problem with that. The software also allows for control over individual printers, so you can be miles and miles away and you can remotely monitor it. There's also plugins for camera controls, which is really nice, so you can watch the print as it's happening to make sure nothing's wrong on that end. This also means that you can move the print bed, you can move the head up and down, you can change temperature and whatnot on the fly. The FANUC communicates successfully with the server. The build plates are in fact removable magnetic surface, and the FANUC can reach every single work object that it needs to interact with it appropriately.
So our project has some societal implications. It provides a lot of classroom benefits, which was our main goal in implementing the project, because it allows students to participate in the entire engineering process from design to completed part. It also allows for the enhancement of learning aids, particularly in special education settings where it's too expensive to provide custom parts. Educators can print them themselves. It also better prepares students for the future, since more and more we are focusing on automation in our manufacturing processes. This allows them to see what automated manufacturing looks like earlier on in life. It also encourages change in the education curriculum. By having these sorts of supplies, you can move the curriculum towards a more hands-on based experience. Next steps include addressing printer vibration issues. Right now, it's affecting our prints a little bit, and we would rather that it future goal so that somebody doesn't have to replace the filament themselves. We also would want vision-based quality tests. That way people can see how well their print is doing before they come to pick it up. They can stop it in progress if they have to. We would also want to design a system for indefinite expansion. Right now we can only serve 3 printers. We would want to expand our system so that no matter how many printers you have, we would still be able to serve it. And we would also want to refit the system with a different robotic arm. The FANUC, while we could use it for our purposes, is fairly old. It doesn't have a lot of support anymore, and it is too expensive for educational settings.
So I'd like to start the Q&A session. I'm also going to put up a video in the background here. We'll just load that up just so you can see. It's going to be a muted video of the robot moving around. I'll just go ahead and move that actually. So with that, questions?
What modifications did you do to the printer to make sure so you could remove the bed and use it in this?
To modify it, the first thing to do when we originally got it, it had a piece of build surface on it. We had to remove that. We also added onto it a magnetic base plate, which was a piece of aluminum with 5 magnets, and that you can see there is mounted with the original 4 screws that are set onto the heat bed onto the line axis. The other modification would be the print bed, which was a piece of steel with a piece of PI on top.
Yeah, you said the future modifications would be to address the printer vibration, but was that didn't have to do with what you were doing? Was that just because of the quality of the?
Yes, I was referring to print. That was referring to print quality.
Yeah, that would entail on my own personal printer at home. How I resolved that is I designed a vibration dampening system that essentially uses foam balls under the feet of the printer. It wouldn't work in this situation because it's simply too large, but you would have a absorbing material such as a spring or foam system that you'd have to put between the printer and whatever surface it's resting on. It just needs to be addressed in the next.
Any other? Yep. Another question?
Just watching the video here, when it slides on the tray after you deposit it, what prevents, I guess, backup? Is there another user there that removes the trays and does something with the products? Or what
Yeah.
happens after it drops the tray with the print on?
Yes, a human actor would come in and remove the part from the print bed, and then once the operation is done, it's put the print bed back onto the shelf so that can get it. The PI is special in that once the part has cooled, it's actually very easy to remove off the PI.
So in theory, could you, I guess, continue the system with another arm that would remove the print bed and the object, and then put the print bed back to a location where this arm could get it and reset it back on the printer?
Yeah, certainly.
As
Yes.
one full cyclical system?
Yeah, especially with vision controls and OpenCV, you could absolutely design a system that can recognize, because of these printed parts, especially the more vibrant colors, stand out against the print surface. So you could absolutely design a system that can recognize the printed part and pull it off after it moves in.
Okay.
Okay, let's give our speakers a nice round of applause. Thank you.